Hello, everyone. I am Renee Yager. I'm the Director of Marketing at EPC, and welcome to today's Summer of GaN webinar, GaN First Time Right, Web-Based Design Tools to Accelerate Your Time to Market. Before we get started, just a few housekeeping items. You will have the opportunity to submit text questions to the panel by typing your questions into the Q&A feature at the bottom of your screen. You can send those in at any time, and we will collect them and address them during the Q&A session at the end of today's presentation. So without further ado, I will introduce our speaker today. Andrea Gorgerino is EPC's Director of Global Field Application Engineering. Andrea is an engineering leader with several years of professional experience in leading design and development of power electronics products, including hardware and firmware. Andrea, thanks for joining us today.
All right, thanks, Renee. Hello, everybody. So welcome to this webinar. And as Renee mentioned, the topic today is the web-based design tools from EPC. So let's jump right in. So first of all, there was in the title GaN First Time Right. So just a quick slide on what is GaN First Time Right. This is our internal initiative to organize the material that EPC has generated over the years to support design engineers in implementing GaN solutions to make it more easy for them to find the material. So the thought process is to organize the material and the tools into a similar process to what a design engineer will do when implementing a GaN in their solutions. So you see here, we've split it into 8 steps from the very research initial stage through the design to the evaluation. And all the material is organized in these pages, and including in this is some of the tools that we have developed over the years to support design engineers in utilizing and implementing GaN in their solutions. So in particular, a lot of the tools that we have are really geared towards the step of selecting the right device, right? It's about comparing devices. It's about understanding trade-offs and doing trade-off analysis. And we'll talk a lot about this part of the web-based design tools. Of course, these tools can also be utilized for more detailed analysis, like loss calculation and thermal management. And especially some of the tools like the SPICE simulations, for example, can provide quite detailed analysis in terms of losses and electrical behavior. However, to really be able to go to the design level accuracy required in these phases, there's a lot of extra work that needs to be done. And some of the tools are actually require more specific analysis than some of the more generic web-based tools. So again, they provide a good starting point for some of these more detailed analysis, but there's definitely some additional steps that need to be implemented to get the accuracy required. So let's jump right in. So we'll start introducing the tools, and then we'll go for an example of how we can use them. All right. So the first tool I'm going to talk about is our cross-reference tool. So a cross-reference tool is it's very common in the industry. You might have used some of them from various semiconductor manufacturers. However, we took a very different approach. So the typical cross-reference tool that you'll find in power electronics is usually based on a few parametrics, basically the breakdown voltage. It'll do a filter on the package, so mechanical compatibility, and then a few parameters, mainly RDS(on). And this can be effective for silicon MOSFETs, which have been there for a long time, are quite standardized, and a lot of similar performance from different manufacturers. You can find many part numbers, but at the end, relatively similar performance. Of course, GaN is completely different than that. So we took a different approach. And the idea of this cross-reference tool is to provide some recommendation on GaN devices that will have similar, better performance to a silicon MOSFET. So of course, since they're not the same and they're not pin-to-pin compatible, we took a more systems level approach. So the way we did that, we partnered with the Discovery. What they did, they created a database, very large database of pretty much every MOSFET that's out there, 20,000 MOSFET, 28 manufacturers. So if you're using a silicon MOSFET today, chances are it's in the database. And they've digitize the data sheets. So we have all this information available, and we take advantage of that by basically doing a power loss calculation, actually a first step of a design analysis in a specific set of conditions, and looking at that silicon MOSFET and then comparing it to GaN FETs and selecting the ones that offer better performance, and showing those analysis there. So we show those 4 or 5 part numbers that have better performance in terms of power loss in a specific set of conditions. The other thing that's interesting is we also link this tool to DigiKey. So we also pull in the DigiKey pricing for all these parts, the silicon part and the GaN FETs. And what you'll find is most cases, you'll see that we can offer products that have better performance as well as having lower cost or lower price. I think that's very eye-opening for a lot of users that first time look at this kind of tool. Another thing that I want to highlight is that this tool is also very useful because it does it really simplifies some of the first steps that you do when you're looking at new components, which is the datasheet comparison. If you look at datasheets, everybody makes them, but they're all different conditions. So it's actually very time consuming to try and do an apples to apples comparison. So we tried to make that process very simple. You'll see here on the bottom right, those are 8 sections that we provide. So it's not just that initial comparison with the power loss, but there's a very detailed analysis in there in terms of various figure of merits, losses, ID and PD, switching times, and all of those are done in same conditions. So they are recalculated for each of the device in the same conditions. So you can really have an apples to apples comparison on top of having the datasheet tables. So quite useful. You got to scroll down the page. Please do. There's a lot of things in there. So I think it really simplifies that initial phase of just understanding the components, how they compare based on the datasheet. So once you have this first level recommendation, what you can do, we have another tool on the website, which is a very simple tool. It's a Synchronous buck tool. This is also based very similar to the previous one on formulas from the datasheet, right? So this is very common in industry. There's various flavors of it, but basically it's the same idea. You take the datasheet tables and figures, and there's a set of formulas so you can calculate losses. The difference on this tool versus the previous one is, of course, it's more specific. There's a topology here. The previous one was really more generic. This one has a half bridge, basically a buck tool. And the reason we have this one, of course, this is a basic building block that is representative for many different topologies. But since it's a specific topology, you have to enter a few more parameters. But what you get out of it is now you have different calculations, for example, for the high side and low side, because they have different trade-offs in terms of switching and conduction losses, as well as a more detailed loss calculation. So you can really understand how some of the parameters affect different parts of the losses. So once you put the parameters, the tool will do the calculation for the whole portfolio. It will, by default, it will rank it by the lowest losses. But also this tool is linked to the pricing for the EPC GaN FETs. So you can have different filters on parameters as well as pricing. So this also makes basically an opportunity to go a little bit deeper in the analysis of the trade-offs, for example, the part numbers that were shown in from the cross-reference tool. So next level of loss calculation, electrical analysis, for example, can be done with PLECS. We offer PLECS models for our parts. What PLECS does is it offers SPICE-like schematic input tool that allows you to analyze more specifically different kind of topologies, as well as different kind of controls that you would have versus a standard sync buck tool. So EPC, we offer a custom model for our FETs that was developed together with PLECS. it has a couple features. So the first thing, it has 2 ports for the thermals, because all of EPC GaN FETs allow dual-sided cooling. And so this model allows you to take advantage of that. It has 2 output ports, and you can connect to different thermal equivalent circuits to it to represent the 2 paths to the PCB and to the heat sink. It also has some internal logic to allow you a more detailed, automatically a more detailed analysis of different kind of losses, similar to the buck tool I just showed. So you can see, you can have turn on and turn off losses, conduction losses, gate losses, things like that. So of course, we provide an example circuit that shows you how to wire the stuff together. But what this allows you to do is to take the analysis a little bit step deeper, right? So now you can look at different topologies and different control argument and still get that trade-off, that understanding of the trade-off that different parameters and different parameters can give you in terms of different components to the losses. I do want to say a note here that no, PLECS uses, it does circuit simulation. However, it does not do the transient simulation. So the switching losses are not simulated. They just assume ideal transition. And there are some tables that will calculate the losses. And that's what we provide. We provide these tables. The tables we provide are calculated based on very similar formulas to the previous tools that I've shown, right? So based on datasheet parameters. But they are done with the fundamental assumption of having a symmetrical half bridge. This is something that in the previous tool, for example, you could have different high side and low side. In this case, we have to make, because of how the tool is implemented, we have to make a choice. This is a choice that we make. So be careful in using this. Of course, you can draw any schematic that you want in the PLECS, and it will give you a number. However, the models that we put in are for that particular case, symmetrical half bridge. So if you have a different configuration, asymmetrical in particular, then you would have to regenerate those loss models. They're not valid anymore. In particular, I'm talking about the capacitive loss components. But except for that limitation, again, this allows you to go a little bit further in the analysis of behavior of the devices. To go even deeper, then of course you go to the SPICE tools. SPICE tools are very important. So what the SPICE in general, what they provide is, versus the previous tools that are all based on some approximation of the behavior using tables and graphs from the datasheet, this tool, of course, has a continuous model for the GaN FETs as well as for the circuit. So this is a continuous approximation. There's no approximation. It's a continuous model for the GaN FET itself. And this provides a lot more accuracy when it is solved. Of course, it requires more time for the simulation. But not only that, of course, it has the flexibility to put whatever circuit you want. And it doesn't have the limitation that I was talking about in PLECS about the initial assumption. The model is calculated for whatever topology you're putting in there. It also has the advantage you can put models of what is around the GaN FETs. And that's very important for GaN. GaN is a very good device, a very fast device. So its performance is actually very much affected by what sits around it. So the first thing is the gate driver. The gate driver model is very important, and you need to take that into account. The next is parasitics of the PCB. Now, there's many parasitics. The main one that really you should always think about when you design with GaN is the common source inductance. Common source inductance is really important. Our devices have almost no internal common source inductance. You can see the packages behind me here. These are all chip scale packages. We also have some QFNs, but they're all very similar. There's no wire bonds. So internally, you have almost direct access to that source terminal. However, you have to implement that layout somehow in your PCB. And there's a minimum amount of common source inductance that even with the best layout you will have, and that will have an impact on performance, on switching performance, because it's a basic negative key feedback on the gate loop, right? So the faster you switch, the more your voltage drop you'll have. It lacks kind of like an additional gate resistor and can be significant when you're switching fast, which GaN FETs do. On top of that, of course, you can add the passive components and their parasitics. That's very important, especially when you talk about efficiency, especially when you talk about inductance. At a minimum, the DCR will have a huge impact on the overall efficiency. That should be included here. So in EPC, the main tool that we use is LT-SPICE since the beginning. So we have a full library. We do support these additional models you see listed here. but the main one where all of them are derived from an LT-SPICE. And in LT-SPICE, we provide not only the models, the library models, but we also provide an example model here. Again, it's the standard half bridge as before, but it has a couple nice features that make the initial analysis very quick and very helpful. So first of all, it has built-in PWM generators. So you only input application parameters. You don't have to deal with the timings and calculating all those things. So all are pre-calculated. So you just put the same inputs as you do for the other types of tools that were shown before. Second, I mentioned the gate driver. There's a built-in simplified gate driver model, which is simply the gate resistors. But the way it's implemented, this section here in the middle can be easily replaced with a full SPICE model of a gate driver, which I highly recommend if it's available. So for example, ADI Analog, of course, they own SPICE. So their GaN gate drivers have models that can be directly plugged in here, and they provide much better simulation results, more accurate results if you do that. And then finally, on the circuit model itself, and we include not just the circuit model, but also some initial parasitics. Of course, this is very generic, so it's not valid everywhere. But in particular, we include a common source inductance, which is a typical number, but it's a very good starting point for the analysis. And I really recommend using the default if there's no better choice rather than 0. It will provide, again, better results. We also include some parasitics for the PCB traces itself. Again, this has a lot of variability depending on your implementation, but at least it's a starting point for your analysis. And finally, we have this loss analysis via the dot mesh, which is basically allowing you to get automatically all the details that we got in the previous tools. So the split between switching loss and conduction loss, the turn on, turn off. This will also calculate actually rise and fall times automatically for you and DVDTs, all without actually doing any measurements. So it's in the log file, you just run it and go from there. So this gets you the advantages of the accuracy and the more detailed modeling of a SPICE tool with the ease of use of some of these other web tools. Of course, simulation time is a little bit longer. You know, typically, actually, if you run this typical circuit, it's like 20, 30 seconds, so it's not that bad at all. And you get the same level of detailed results without having to analyze by itself, which actually can be very, very time consuming if you do it by hand. So those were the electrical tools. And of course, like power electronics, we always have to think about temperature, thermals. So we do offer what we call our thermal online thermal calculator. And what this is an extremely flexible and powerful tool. It is based on internally, of course, we use finite element analysis models. In many cases internally, but they're very time consuming. So we made an effort of simulating many different use cases and then use a parameterization of those results and implemented them in this tool. So what this tool allows you to give is without having a detailed design. So to use an finite element analysis tools, you need to have a real PCB layout implemented, right? Or heatsink or anything, a real design. So in this case, you can put some parameters for your design, but you don't need the real design. So you need a thermal concept. You don't need a full thermal design. And what you get is the result is basically the analysis of that thermal concept. And this is useful because at this stage, this is usually an iterative process where you go through the previous tools, electrical tool, get some loss numbers, plug them in here, see if they work, go back and fine tune your device selection. So it's important that this is done quickly and then you don't have to redesign everything every single time. So what the tool supports basically pretty much any thermal concept you can think of. So mainly there's a PCB cooling options, right? It's very common. You can see the actual illustration here on the right-hand side that has all of them. So PCB cooling stores the bottom, and you have an ability to input the vias, the layers, and the airflow for that, because those are the main parameters that will affect the PCB cooling, as well as heatsink cooling. And the parameters that you can affect there are the thermal interface material, extremely important, the heat spreader, the heatsink. We also have a heatsink calculator actually there if you want to input it as a requirement, as well as the airflow. And we actually also have a third one I didn't really put it as bullet point, which is a barrier, like a constant barrier option. And what that allows you to simulate is if you have some liquid cooled heat sinks, for example. Of course, a little more advanced topic. But basically, with very few input parameters, you can get a good idea of how your thermal concept will work and if the device will work or not. And the outputs that you get are basically two. So first one is you get the temperature of the devices. But the second one is also very useful, is you get the parameters for the simplified thermal model. You can see here the schematics, the resistances, for example, RTH. This is in the case where you have the top side cooling, the bottom side cooling, and mutual heating. So you get the values of all the resistances, and that can also be very useful for further analysis in different simulation tools to get more detailed results. So again, very helpful to be iterating between this tool and the previous power loss tools. Okay. But at the end of the day, these are all calculations. So I really want to stress a really important part of our tools is actually our hardware. So we offer a lot of hardware for our parts, and this is extremely important. Because I mentioned CAM devices are very good. They switch very fast. At the end of the day, they're very much affected what sits around it. And there's just so much you can do in simulation. In the real hardware, you really get the real results. So we offer mainly two types of reference designs, demo boards. The first one is the 90 family of boards. And there's a picture that I have here on the top. It's an example APC 90153 for the 2619. And this is a basic building block. It's a half bridge with a gauge driver, lots of the test points to do measurements. It has some big pads for you to add your inductor, whatever it is in your application. The latest generation ones also have some mountings for a heatsink to allow the exploration of different thermal cooling solutions. And this is really the fastest way to validate the calculation that you did in previous steps, right? It's not a full application, but allows you to test in a condition that is representative of your final application. And this is really important in my eyes to validate the device selection. Now, we also offer the 91 series of demo boards, and these are more application-specific designs, right? So we offer them for various different applications, DC-DC, motor drives, and LiDAR, and wireless powers, and we just recently released a Class D one, for example. So, of course, these get you much closer to the application. You can do real-world testing, maybe even driving your own loads. Although, of course, now when you get specific, you might not have exactly the same conditions as you need. The picture I'm showing here is actually for the 9159. This is a very extremely high power density converter. This is a very small, it's a 1 kilowatt LLC converter. And again, it's an example to show, basically to showcase what you can achieve with GaN. Now, of course, these are closer to the end system, so they're sometimes not as easy to measure as well as modify for your own conditions, right? Versus the 90 family. We also have a lot of partners that are making reference designs with our parts. I've highlighted here two of them, Renesas and ADI. They made quite a few of them because they actually have a whole family of controllers that are meant to be used with our GaN FETs. And when they release their controllers, they will make these various reference designs, various different end application targets using our GaN FETs. So we try to maintain our list on our website. You can find it there. And these are two examples. Those are also, of course, very useful, especially for DC-DC, I would say. Having controllers meant for GaN really can make your designs faster and easier to implement. So those are the overview of the tools. And right now, I would like to give you an example and just walk you through a little bit how they work with some real numbers. So I'm just going to start with just going to use a very simple case. And one of the reasons I'm using this one, by the way, is because we actually built boards for it, and so I can show you some real results at the end of how it looks. But we'll just assume that we have very standard buck converter, 48 to 12 volt, running at 300 kilohertz, about 260 watt, that's 22 amps. And it's using this on part 80 volt, 2.2 milliohm. It's a silicon MOSFET, latest generation. And the goal that we have is we want to increase the switching frequency, and we want to use these tools to understand what the value of GaN is in this particular application. So our target is 500 kilohertz, right? Let's see what we can get. So the first thing is we'll go in the cross-reference tool. So we'll plug in the number, the part number from on, and you can see here, this is just the top page that you presented, and you have these 5 options here. So first thing you'll notice is that the tool automatically selects these conditions for you, right? And these are based on the silicon MOSFET that you decide. And in this case, it shows basically 300 kilohertz and 30 amps and just 50% duty cycle as an approximation. Okay, that's actually not that far from what we were doing. It's not exactly the same. But with those conditions, this is what you get. Just gonna, again, this tools offer lots of tables, but really just focus on this one here, which is the calculated total power loss. This is, of course, there's no topology in here, but it's a representation of a hard switching device in those conditions. And the first thing you notice is that roughly you get maybe half the losses using GaN, depending on which device you select. The other thing is you can look at the DigiKey pricing that is automatically populated down here. And if you look at just the first 2 columns, the 1K pricing, the GaN FET is actually about 10 cents cheaper. So you get much better losses for a lower price. By the way, also the package area is very representative. You can see the blue area and the yellow area, much smaller size. So looks pretty interesting. So the next step we can do, we can change the conditions, right? So let's change the condition to match more closely what we were doing before. So I've updated the conditions with the parameters we discussed at the beginning, mainly the 500 kilohertz, of course, the duty cycles, things like that. You don't get, it's not too different, the results, right? I think what you get is that one thing I want to notice, again, in this calculated total power loss line, is that the silicon MOSFET losses increase significantly, right? And that's normal. You went from 300 kilohertz to 500 kilohertz. So you went from, I think it was like 6 watts roughly to 8.5 watts. That's a big increase in losses. However, if you look at the GaN FETs, you're still in the same range, right? Maybe a few, less than a watt for sure, maybe half a watt, not even. And that's the first thing to notice when you use GaN, is that the penalty to increase switching frequency is very low, right? And that's one of the benefits, because now you can think about, okay, I can increase the switching frequency in my applications. It's not going to cost me on the device level that much. What can it do? What can it do for the rest of the system? And that's really where the why GaN starts, is by asking that question, what can this increase in switching frequency provide? Now, you can also look at what can the lower losses provide, what can that package area provide, but it's kind of all driven by this ability to switch fast and increase the switching frequency of the application, right? So we have an initial list of devices, all right? And what we can do, we can go to the next tool, which is the SyncBuck tool. And now we can look a little bit more detailed analysis of the behavior of the devices, right? So again, this is a differentiated tool, so you get different results for the high side and low side. We could even pick different high side and low side if we wanted. In this case, we're just going to stick to a symmetrical configuration for ease of explanation. But anyway, you put in the parameters and you get this more detailed loss analysis, and you get it for all the parts of EPC. So I've plotted here in the 2 charts at the bottom just the devices that were selected, that were recommended by the cross-reference tool. And you see on the left the control FET and the sync FET as a function of RDS on. And the first thing to notice is on the sync FET, it is very well correlated, right? It's mainly conduction losses at the end on the low side. So low RDS on will give you lower losses. However, on the left-hand side, it is not at all correlated. You almost see a flat line. So the figure of merit of the device, its generation, is very important. I just want to highlight that when I generated these charts, because this tool, as I mentioned, allows you to have different high side and different low sides, the actual EOSS losses are calculated separately for high side and low side. When you actually assess the losses, the low side EOSS losses are actually dissipated by the high side. So when I plotted this chart, I took the USS from the low side and moved them to the high side. And to have a better analysis, you should try and implement that in your analysis. So the only thing I want to highlight in this chart really is the 2619. And 2619 is our Gen 6 device. It's our latest generation device. And what is interesting about it, it is actually the same size as the 2204. And this highlights what the progress in generations in GaN can give you, where you have the same die size and you have this massive improvement of figure of merit and RDS(on), and this translates in a very large improvement of performance. So I think so we'll pick the 2619. It's our latest generation device, and we'll see what it can do for us in the next steps. So the next step is the more detailed loss analysis. Like I mentioned, SPICE. SPICE would be the next one. And it's very easy to implement this. Just download our library. It has the example circuit in there. All you got to do is type in the part number, and you get all the losses already in the log file there. And what you notice, and you can look at trade-offs, you can look at many trade-offs, different things like gate resistors, different gate drivers, and of course different conditions, and very easy to implement. So I only looked at one thing here though, which is the common source inductance. I mentioned in the beginning why it's so important. So in the charts here that I've plotted in blue the original results that we got from the previous tool, a SyncBuck tool, and I've plotted in red and green the results from SPICE using 50 and 100 picohenry. And you can see that on the control FET, which is the one that is doing the hard switching, it's a very big difference, right? It's really significant. On 2619, you go from 1.5, 1.6 to basically 2.7. So 2.7 is 100 picohenry. That's the default that we have in the tool when you download the example. You can probably do better if you do a really optimized layout, but you see at the end between 50 and 100, actually the difference is not that big. So we use that as a default. It's a good starting point. It gives an idea where you're going to end up. So it's important, I think, that you don't skip on this step and just use the previous tool. Previous tools are good to get you the device. Again, you don't necessarily want to do SPICE simulation on all the devices from EPC, but to go to the next step, this SPICE simulation, I think, is important to provide you more accurate results. And fine, now that we have an idea what the losses will be, we need to do the verification on the thermals. So the first thing you can do, of course, you can just look at the datasheet. So the datasheet has some thermal information. That's very common. This is what we provide on our datasheet. There's 4 numbers in there. I'll just walk you through them real quick. So the first one is the junction to case. So this represents, we have a little bit different nomenclature than a lot of semiconductor companies. Our case is basically the top of the device. That's where you would attach a heatsink for dual-sided cooling. Of course, this is the best way to take advantage of the power density of GaN. You get the higher power density designs by using dual-sided cooling, and that's because you can see from this table, that's the lowest number. It's 1 degree C per watt for, in this case, a very small device. The next line is the junction to board. It's the PCB side, the bottom of the device. And this is the number you would use if you're using PCB only cooling. Now, this number is not that useful because the reality is when you use PCB cooling, the large contribution comes from the PCB itself, right? So having 2.6 does not tell me much on if the device is going to work or not in my applications. So that's why we have the last 2 numbers in there. So the third one is the R theta junction to ambient, right? So now this is a number I can use because it is all the way to ambient. And this is done for a standard JEDEC condition, right? So this is a PCB cooling only path with in a natural convection for a predetermined size and type of PCB. However, this is also, in my opinion, not that useful. I mean, it's useful to compare different parts because it's a standard, and you will find this number also given from some silicon MOSFET, not all of them. So it's nice to be able to compare, but it's not that useful, I think, to actually know is it going to work for me or not, because there's no real layout. It's not a real PCB, right? So that's why we provide the last line on this table. So this is the real R theta junction to ambient measured on our evaluation board, right? This is the, like I mentioned before, the EPC 90153 for the 2619. This is a real board, and this is the number that you get for that board. And so we can start with that. So let's start with 46. Let's plug in the numbers. And what you get is very high delta T's, 100, 124. So obviously, in a natural convection environment, this is probably not going to work in most design. This is too hot. So we need to take a look at the next steps. What kind of thermal concept do we need to do this design? And so that's where the thermal tool comes in, right? So we can use the thermal tool to understand the trade-offs and what we need to do to implement. So the thermal tool is very easy to use. You have a few application conditions, right? So first is the configuration. You can have a single device, two device symmetrical, or two asymmetrical device. This covers pretty much all the concepts you can have in power conversions. Then, of course, you can select the device itself and the losses. So the losses, they just come from the SPICE simulation we just did before. So I take the numbers that I had from the SPICE simulations and plug them in here, okay? So once you have that, then you need to define the thermal concept. So here in this example, I'm only going to do PCB cooling first, but you have similar set of questions in case you want to use a heat sink. So in our case, we're going to use start with the PCB information. So of course, if you already have a fairly detailed PCB concept yourself, you can use that information. Usually at this stage of the design, you might not be there. You're really doing the first step of device selection. So, but what you can do, again, you can use the parameters from our half-bridge demo board, which has all this information. It's a real design. It's implemented. You know, it's easy to copy, by the way. We recommend you that you copy it. You can use those to start with. And that is mainly, so first of all, we'll start with the spacing, right? How far apart the devices are. And that's easy to measure. And then you have the number of vias of each device. So I took a snapshot here from the Gerbers showing the vias for the high side and the low side. You can see my mouse, it's right here. And it's basically 10 for the high side, that's the FET on the top, and 18 for the low side. Just a quick note, why is it different? And the reason is because in this design, we're implementing an optimized power loop design, where the capacitors, the decoupling capacitor for this half bridge are placed on top of these FETs, on the top layer above these two FETs here. And so the loop itself is closing in the first inner layer right below these FETs. So it goes at the bottom, you can see the bottom vias here, then goes on the first layer, goes in and goes back up for the caps. Now we want that current to flow right beneath the devices to allow this inductance to be minimum. And if we don't remove those vias, if we have the full vias on the high side FET, the current will actually have to go around the FET because there's no room for it to go through. So that's why we remove those two lines of FET, the vias in the top side FET, and that's why the top side FET has fewer vias. Now, there are different ways to do it. And if you go on our GaN First Time Right page on layout, you will see a lot of different examples and trade-offs, how to do layouts, how to implement them. And there's also some options where you can actually space these more apart and have full vias for both high side and low side. So there's examples there. But in this case, this is how we implement it. And so that's what we plug in, 10 and 18. And finally, we need to provide some information on the PCB itself. Again, the stack up is provided in the files for the board. In this case, it's a 6-layer board, 2-ounce copper, and it's 2 by 2 inches, 50 millimeters, basically. And so that's the parameters that you need for the PCB. Again, no detailed design, just high-level concepts of how you're going to implement the design itself. The last one, and that's what we're going to look at in terms of trade-offs, is you have the airflow. So we already looked at that we can't do it with zero airflow. So let's take a look at what airflow can do for us. And you can use this tool to do various trade-off analysis, right? In terms of PCB and heat sink, high side and low side, neutral heating. The main one we're going to look at here is the airflow. And so I plotted that chart on the right-hand side. These are the results that come out of the tool. And the point at 0 LFN, that's 0 airflow, that comes from the datasheet, right? That's the number we looked before. We know that doesn't work. But the blue, the junction to ambient curve, shows you that if you start adding airflow, you can actually decrease that RTH significantly. And as an example, on the bottom, I've plotted you with 400 LFM, what the tool says, basically you get around 50 degrees delta T, which is now very reasonable. I think this is a good design point. This is definitely worth trying it out. I do want to highlight another interesting thing that this tool gives you, which is, as I mentioned before, the parameters for the simplified thermal model. In this case, we only use PCB cooling. So we only have 3 parameters, which is the self-heating of the 2 devices and then the mutual heating of the 2 devices. And in the chart, that's what I've plotted in red. In red, I have the mutual heating. And the mutual heating, a couple interesting things to note is first order is not really dependent on the airflow. It's really depending how good the 2 devices are coupled, how close together they are, for example. And the other interesting thing to notice is that when you have a system that is not very thermally efficient, right? Very low airflow or no airflow, that mutual heating in terms of percentage is fairly low, right? If you look at 0 LFM, you're comparing 44 with about 10, right? 12 maybe. So less than 20% of the rise of the device will come from the heat of the device next door. But if you increase the airflow and you decrease the junction to ambient cell of the self, you'll get that for 1000 LFM, the two are actually equivalent. So you'll get a same amount of temperature junction increase because of the self-heating and because of the mutual heating. And that's where a tool like this can help, because you can now look at different spacing, for example, and maybe decrease that mutual heating if that's a limitation. In our case, we're just going to leave it like this and go on with these numbers, right? And what the next step is, as I mentioned, you have to test it out, right? And so the best way to do it is with the half-bridge board, the 90 family, that you see the picture here on the left-hand side, with the mounted inductor on the pads. This is the fastest way. Again, it doesn't necessarily have to represent your exact application, but it can represent the condition, for example, where you did the simulation previously. And also on the left-hand side, you have the board for the 2619. That's the device we were looking at. And on the right-hand side, we have the on-semi part. So in this case, we don't build these normally, but we built one as close as possible as the 2619 one. So you can notice the big 5x6 black silicon MOSFET here. We did have to move the gate driver to the other side just to make it fit because it's so much larger. But the size and the construction is very, very similar. And so we have some results. And what you see here is basically the chart showing both efficiency and losses of the power stage, which is basically the FETs and the inductor. So please notice the inductor was not included in the previous analysis of the losses. That's why the numbers are a little bit different also. But it confirms what we have discussed. So at 500 kilohertz, it's the blue curve and the orange curve, and you can see much higher efficiency, much lower losses. You can also see so much lower losses that if you actually do the measurement at 1 megahertz, that's the green curve, you still have lower losses than the silicon MOSFET at 500 kilohertz. And that's where I was mentioning before, the trade-off of switching losses really opens up what you can do in your system to take advantage of that. Another thing that we're highlighting here, of course, is that since you have lower losses and lower temperatures, you can actually carry more current. So the table shows you with different airflow what the maximum current you can do. And so basically, maybe one way to look at it, with the silicon MOSFET, to do 22 amps at 500 kilohertz, you need 1000 LFM. And with the 2619, you only need 400 LFM, right? And you can look at it many different ways, but the message is saying you can carry more current because it's so much more efficient. All right, so let me show you just a waveform, because once you have a real board, now you can really look also how the thing is switching. And this is always very interesting chart. I like to show it. It basically shows the reason for all this benefits. At the end of the day is how fast you can switch the devices. This is very striking. This is rise and fall times for the switch node, and comparing the silicon MOSFET with the GaN FET, you can see how much the difference is. That's what gives you the lower switching losses, and that's the trade-off that you can do to take advantage at your system level for this increased efficiency. Okay. Finally, I have some temperature plots. Let me just highlight this one. Again, this is done on the middle column, is all done at 22 amps, which was our initial conditions. And you can see that in the same condition, the GaN is running about 15 degrees cooler than the silicon MOSFET. Okay. Of course, that also means you set the picture on the left, you can carry more current, or like in this picture, you can run at 1 megahertz, which you were not able to do with the silicon MOSFET. It just gets too hot. Okay, so these are just different ways to look at the same trade-off, and you can do it in real hardware because it's basically all of our devices have this kind of half-bridge boards that allows you to do the quick testing in the lab. So in summary, so in the example, we basically went through all the tools, right, to compare the silicon MOS with the GaN FETs. And at the end, we did confirm via real measurement that the 2619 in this case had lower losses, can carry more current, and is also cheaper. Remember the table from the original cross-reference tool than the original silicon MOS, right? So these tools, just in summary, the cross-reference tool, it really is the easiest way at the beginning of your exploration of GaN to compare your existing silicon solution to GaN, and that includes pricing trade-offs, right? Then we offer a lot of loss calculation and simulation tools to provide more refined and gradually more detailed device optimization and trade-off analysis depending on your need, including SPICE, which of course offer the greatest flexibility, but sometimes can be more time consuming. Finally, the thermal tool is a very important part of this tool chain because it's this iterative process. And thanks to the fact that you need very few input parameters, very fast but flexible, and allows you to do these very exploration of various thermal concept, and also here thermal trade-off analysis. Sorry.
All right. Thank you, Andrea. So,
yeah, thank you.
Now we're going to begin answering the questions that have been submitted during the presentation. As a reminder, you can still go ahead and submit your questions by typing them into the Q&A feature at the bottom of the screen, and we'll get to them for you. So, Andrea, our first question is, would you recommend using EPC GaN FETs in series in the case of a 400-volt bus?
No. Just like silicon MOSFET, you cannot use these devices in series, right? The balancing of the voltages is entirely dependent on parasitics, and you cannot control those. So you need to have an active way to control the balancing of the FETs. So what we do offer, basically, we have an example of a reference design using a multi-level topology. That's very common, I would say, in common. It's an approach to do the same thing as putting FETs in series, but do it at the level of the topology, not at the level of the device. So we have an implementation for the CDC converter with 3 levels. We also have a PFC with 4 levels, and all of those basically showcase how you can do exactly what you said, but do it at the topology level. By the way, when you do it that way, it also has a lot of advantages that are very interesting, and we don't have time to go in detail here, but because now you have more levels, you have more freedom in the modulation techniques, which means you can actually reduce the voltage steps on the output. And when you use an inductor as an output, or any load for that matter, that volt-second reduction actually can have a lot of benefits. It's almost like a switching frequency enhancement. So even that topology, on top of having very good devices, low voltage devices that are rated lower, be able to be used for higher voltage application, also has some inherent just topology level advantage, which are really interesting. And we have a couple of examples of that on our website.
On slide 20, can you go back and show where the GaN FETs and the silicon MOSFETs are on each PCB?
Oh yeah, you can. I should have highlighted in red. I forgot about that. You can see this is actually the driver right here, and the 2 high side and low side. These actually, you can see my mouse, right? Yeah. Can you see my mouse?
Yes. Mm-hmm.
Yeah. It's here. Here's the decoupling caps that I was mentioning before. So that's the power loop right here. So the 2 GaN FETs are there, and then on this side, everything is much larger. So you still have the decoupling caps over here, but the 2 FETs are very large. And the gate driver had to go on the back of the board itself. So right here.
Okay. How frequently are the design tools updated to reflect the latest advancements in GaN technology?
Very recently. So every time we release a new product, I think we update all of the tools. So the cross-referencing tools is updated monthly with all new GaN FETs as well as new silicon MOSFETs. So all the latest generation devices that all the silicon semiconductor manufacturers are releasing once a month are updated in the tool. So you should find really the latest and greatest as well as old ones in there. Our internal tools like the Buck tool, Spice tool, every time we release a new product, it's in there, including the thermal tool. So yes, all of them are very up to date.
Do these tools account for worst case scenarios or stress testing for GaN devices?
So worst case scenario, no. So these are pretty much all based on typical values. And the reason is, as I mentioned before, these are meant really mainly as a selection device, right? If you want to do detailed design analysis, you really need to have a much more accurate prediction capability before you do a worst case analysis. And that detailed matching of measurements and simulation requires really basically an optimization for the specific use case, right? So I'm thinking about Spice, right? Spice by itself will give you a number, but it's not going to match your real number unless you model your full system, right? Including all the parasitic. I mentioned some of them, but if you want to really get a good matching, you need to really include all of the models for all of the components that really are relevant for the power conversion stage. Once you have that, then you can use Spice tools to do worst case, but yeah, that's not implemented as of today.
Where is the circular inductor / magnetics on the silicon board?
This is the inductor, big gray box here. So we use a large one, so we try not to contribute to the self-heating of the board in this case.
Okay. Could you show on the website where to select each of the tools you talked about?
Yes, I guess I could. Let's go on the website. So I think the easiest way is you scroll down here and you will find the first one is the cross-reference tool. It's hard to miss. There's a big red cross on the MOSFETs. And this is how it looks like. And I probably have a few part numbers already there. That's what I used recently. And then you just get the table. So you can see here, you can scroll down, you get even more information. You can go here and you can change the conditions. You can, by the way, I didn't mention this, you can use hard switching, soft switching. You can update the calculations with the conditions that you change, or you can get a new recommendation depending on that. So that's where you can find the cross-reference. That's the easiest way. By the way, it's also on the top here. You can just do cross-reference in the search bar. But let's go back to the front page. There's several ways to get. I like to start designing. This is our GaN first time right page. So you can find a lot of the information here. So for example, like I said, selecting the right. I clicked the wrong thing. I don't know how to get rid of it. If you click on selecting the right device, you go to the page here and you will find a link to the tools. For example, the GaN FET selection tool, the thermal calculator, and various other things. So the other way to look at it, you can get there, of course, is from design support. We have the GaN Power Bench page, and this lists the tool there. And for the models, the Spice models, they're actually all on under design support on the device models, right? And you'll find here, they're also, this is also linked on the product page of each device. And you can see here all the parts. You'll find the various models for the various tools that we offer. In particular, LT-Spice, it's a single zip file that has one lib file that has all the models for all the parts, and one example circuit that is the one that I showed in the presentation.
Okay. How easily can designs created in the Buck calculator be integrated into larger system level simulations?
To do that, my recommendation would be to use, so you can get the numbers, but of course, usually when you're thinking about system level tools, you want to do trade-off analysis and other analysis. So for example, probably the easiest way to do that in the tools that we offer is, for example, Simpless. Simpless is very commonly used for DC-DC power conversion in general, and because it has a more simplified approach and can do more system level analysis. So that's a good tool to use. We offer models for that. PLECS is an excellent tool. It's really what it's meant for. PLECS is really a system level tool. It's very commonly used in motor drives. So we have models for that. You can use SPICE, of course. SPICE is a very detailed tool. So it gets slow if you really simulate the whole system. So for SPICE, you might use it to generate some intermediate steps to generate something that your system level analysis would require. And that's the same way you would use the buck tool, but I would recommend using SPICE for that. It gives you a little bit more accuracy.
Right. All right. Well, that was the last question. So first, thank you, Andrea, and thank you for everyone for attending today's webinar. If you do have any other questions, please feel free to reach out to us. You can send them in to info@epc-co.com or click on one of the Ask a GaN Expert icons that you see around the website. So you should receive a follow-up email in 24 to 48 hours, which will have a link to view a recording of today's webinar. So without nothing else, then thank you for joining us today and enjoy the rest of your day. Thanks, Andrea.
Thank you. Bye-bye.
Bye.